Mobile communication faces two main challenges. One has to do with the tremendous success of smartphones and the respective data traffic that is generated by these devices. At the moment, the total traffic that is sent through mobile networks doubles almost every year. In order to address that challenge, we would have to allocate more radio frequency spectrum to these networks, but we simply don't have that spectrum available. So one way to solve that issue would be to make these systems more efficient, more spectrum efficient, which means we squeeze out more bits per hertz bandwidth. This is a challenging task. The second challenge we have is to make these systems more energy efficient. At the moment, we have about 1.5 million cellular radio base stations deployed worldwide, and these base stations consume a lot of energy. The total amount of energy that is consumed by these networks is about equivalent or comparable to that of the entire air traffic. And now what we've done in our lab, we have developed new technology that addresses both of these challenges. And the technology we've developed is called spatial modulation. I'm going to explain to you now how spatial modulation works in principle. For mobile communications, we require a transmit antenna, and we would require a receive antenna. This would define the transmission link, and obviously we want to transmit information. Let's assume we want to transmit the first 4 letters of the alphabet, say A, B, C, D. The way we would transmit that is using signals. Let's assume we have a signal space made of a real part and an imaginary part. What we would do now is we would link these symbols to so-called constellation points in that complex diagram. We would allocate this point as symbol A, symbol B, C, and D. Now we have 4 different signals and 4 different constellation points, and every time we use that channel, we would transmit only one of these 4 symbols. So let's assume we have multiple antennas available at the transmitter. So we have a second antenna, a third one, and a fourth one. These antennas have unique positions on that antenna array, and let's define or let's exploit that fact in defining the location as a spatial constellation point. So like we have defined signal constellation points, we have defined spatial constellation points now. And we say that, for example, that position here, that first antenna is linked to, again, the same symbol A, the second antenna to symbol B, third C, and the fourth antenna to symbol D. So essentially what we have created now is a 3-dimensional constellation diagram. And we can extend that diagram here into a 3rd dimension. It's called space, where we have the antenna constellation points, or spatial constellation points put here. And we repeat that. Say this is A, this is B, C, and this is D. Now let's assume we want to transmit a random sequence of symbols. Say we want to transmit B, A, C, C. The way how it works is that we now would group these symbols into pairs of 2. This is our first pair, and this is our second pair. And we would define the first symbol as the one that is transmitted in the spatial domain. So we mark it red. And the second symbol in that group would be transmitted in the signal domain. So we mark it blue. The same here. The first symbol would be transmitted in the spatial domain, C. And the second symbol in that group, again, in the signal domain. And now, at every transmission step, we would transmit 2 symbols instead of only 1 symbol. For example, at time instance T1, we would transmit B and A simultaneously. At time instance T2, we would transmit the 2 C's instantaneously. In that way, we have doubled the capacity of the system. So what we have here are the principal block diagrams of spatial modulation and conventional MIMO systems. What we notice is that in spatial modulation we require only a single RF chain, whereas in conventional MIMO systems we require multiple RF chains. What this diagram shows is the energy efficiency versus the ergodic capacity for a system that is composed of 8 transmit antennas and 1 receive antenna. What we notice here is that spatial modulation is significantly more energy efficient compared to all the other MIMO systems. For example, if we take a capacity of 150 megabits per second, spatial modulation achieves more than 1.2 megabits per second per joule, whereas all the other classical MIMO systems achieve only about 0.2 megabits per second per joule. What this diagram shows is a comparison of the relative computational complexity of spatial modulation compared to a conventional MIMO system. On the x-axis we show the number of transmit antennas in the system. If, for example, we look at 128 antennas, we notice that spatial modulation achieves a complexity reduction of about 98%.
This production is brought to you by the University of Edinburgh.